Okay, 1973 BC 19, we're asked which of the following series converge. Now the first one, we can tell 1 is a p-series, p greater than 1, so that converges. The second one is a p-series, it's the harmonic series, which we know diverges, but we could say that it's a p-series p equal 1 diverges. Remember that p has to be greater than 1. And for the third, all of these are kinds of p-series here, but the third one is also an alternating series. So that's going to trump everything else. And alternating series are pretty easy to detect whether they converge or not. If it weren't alternating, it would be a p-series with p equal to 1/2, and it would not converge. But since it is alternating, we need to ask 3 questions. 1, strictly alternates, and that it does. Second one is that the absolute value, the term should decrease in absolute value. Decrease in absolute value. And let's see if that's the case. Sure, well, 1 over square root of 1 is more than 1 over square root of 4, which would be 1/2, and that's more than 1 over square root of 9, which would be 1/3. So the terms are decreasing in value, in absolute value. And the third thing is the limit as n approaches infinity of a sub n equal to 0. And there, once again, the square root function increases without bound as n increases without bound, and therefore the ratio will approach 0 as n approaches infinity. And so that it does. So this one does converge by the alternating series test. And so hopefully that's clear. Don't confuse that with a p-series that is not alternating. If it weren't alternating, it would be a p-series with p equal to 1/2 that diverges. But since it converges, since it alternates, it's okay for it to converge. Remember, alternating means you're subtracting values as you go through. So it's very different than a positive term series. And hopefully that makes sense. We'll go on to the next problem in the next video.